Hello and welcome to another statistics video. So today we're having a look at changes to the mean and standard deviation. I've been having some technical problems, so my graphical calculator emulator stopped working, so now I'm using one under a projector, an actual calculator, and my recording software stopped working, so now I'm using Loom, so I apologise for the giant orange dot that will seem to appear at random. I'm not quite sure how to get rid of it. We're having a look at the changes to a mean and standard deviation when we have changes to data, and we're going to have a look first at what actually happens, and we're going to try and come up with some suggestions of how we can generalise it to the general rules that we might come up with. So for the first example, we have a machine is supposed to create ball bearings with a mean diameter of 2 millimeters, and we have a sample of 8 ball bearings which are taken from a production line and they are measured, and then we are told that these are the results that we have here, and we're trying to find the mean and standard deviation of the diameters. So I'm going to put this into my calculator. So we have 2, 2.1, 2, 1.8, 2.4, 2.3, 1.9, 2.1. Remember that we go into calc, set, and because we have a list of values, that means that we don't have any frequencies, so we want that to just say 1. If you don't have a 1 there, like this, then you just click F1 and it'll come up. Then we click exit to go back, and we only have one variable, which is the diameter of the ball bearings, so we go into 1 var. So for our first question there, our mean is 2.075 and our sample standard deviation is 0.1982064, because we were told here that we had a sample. So there is actually a typo here. That should say 0.5 millimeters. And then we have it is later found out that the measuring devices are not calibrated correctly, and all measurements should be 0.5 millimeters longer than they are. What is the new mean and standard deviation of the balls? So instead of having 2, that would be 2.5. Instead of having 2.1, we'd have 2.6. Instead of having 2, we'd have 2.5. Instead of having 1.8, we'd have 2.3. 2.4 would become 2.9. 2.8, 2.4 and 2.6. So then in my calculator I'm going to delete the numbers that I already have in there, and I'm going to type these new ones in instead. So 2.5, 2.6, 2.5, 2.3, 2.9, 2.8, 2.4 and 2.6. Again, we only have a list of data, so I'm going into 1 var, and for that data we've got a mean of 2.575 and a sample standard deviation of 0.1982064. So I'm just going to have a look and see if I can come up with some general rules that might be true. If I have a look at my two means here, when I added 0.5 to each value, my mean has increased. But not only has it increased by 0.5. So it seems that I might be able to suggest that when each value increases by the same amount, the mean also increases by that amount. So we'll have a look later on at another example and we'll see if this is true. If we compare our standard deviations, they've ended up being exactly the same. So it seems that maybe when each value increases by the same amount, the standard deviation stays the same. So we'll have a look later to see if this is true. Having a look at our second examples, now we've got Henry who buys stamps, and this is the information about the prices that he pays, and again we're trying to find the mean and the standard deviation. So I'm going back in my calculator, deleting the data I have in there. So we've got 20 pence, 27 pence, 34 pence and 41 pence. And then we have some frequencies of 24, 39, 50 and 37. Now this time I do have a list of frequencies which I have put into my list too. So when I go into calc, I need to change my set so that it tells the calculator that I put my frequencies into list. So click F2 to get the list option up, and then tell it that you put it into list 2, exit to save that, and exit to go back. Then we're going into one var, which gives us a mean for A of 31.6 recurring, and a standard deviation. Again, this is only 150 stamps that he buys, it's not all the stamps that he ever buys, so we're looking at the sample standard deviation, which gives us 7.147222142. So then we're told that due to inflation the price of each stamp is doubled. So instead of 20p we would have 40p, instead of 27p we would have 52p, instead of 34p we'd have 68p, and instead of 41p we'd have 82p. So then I want to find those new values, so I'm going back in my calculator. My frequencies are staying the same, I'm just doubling the prices, so we'd have 40, 52, 68 and 82. I've already got this set up for a frequency table, so if I go back into one var, we end up with our mean being 62.8, our sample standard deviation ends up being 14.6587064. So we're going to come up with some rules again. So bearing in mind that this here was 6 recurring, if I go back, so then I'm just going to double check that I got that first one correct. I think I did. So it'd be 20, 27, 34 and 41. Yeah. 82, 68, 50. That should be 54. Sorry, not 52. That's why my numbers look a bit funny. That there should say 54. Sorry about that. So actually, we should end up with 63.3 recurring. Just rub those out. There we go. So we should have a mean of 63.3 recurring, and we should have a sample standard deviation of 40.2944428. Now, between our means, it's a bit difficult to tell, but it seems that when we have doubled each value, we have doubled our mean. So I'm suggesting that when each value is multiplied by the same amount, the mean is also multiplied by that amount. Now it's hard to tell with the standard deviation. There's definitely something going on between these two. It becomes much more clear if instead we have a look at the variance. If we have a look at our variance, we have so for the first one we'd have 7.14722.142 squared, which gives us a standard deviation for our first set here, sorry, a variance for our first set here of 51.08277.403. And for the second one, 14.2944428 squared, and that gives us a variance of 204.331095. If I'm trying to see what I have multiplied to get to this value, I can have a look at dividing our 204.33109, dividing that by our variance for the first one, which was 51.08277.403, which gives us almost 4. And the reason why it doesn't give us exactly 4 is that when we put it into our calculator, we're going to have slight rounding issues. Okay, so it's actually the variances that seem to be connected here. So it seems that when each value is multiplied by the same amount, the variance is multiplied. Now I'm going to leave that because there's a couple of ways that I could get from doing times 2 that happened here to doing the times 4 that we've happened here. So it could be that it doubles, it could be that it squares, it could be that we add 2. Okay, so I can't say for certain what I'm assuming is going to happen there yet. However, I do want you to try the 2 questions on the next page and see what you find, and see if the multiplication one can give us more of an idea of what happens when we multiply each value by the same amount. So I'd like you to pause the video if possible and give the Now You Try question a go. So hopefully you've paused the video. I'm not quite sure how to pause this recording though. So I'm just going to have to work through it with you again for these questions. So we've got the data set below is giving in dollars for an electricity store for a cordless phone. So at first we're trying to find the mean and the standard deviation. So I'm going to delete the data that's in there, which gives me 35, 50, 60, 60, 75, 65 and 80. Remember that now we've gone back to a list of data, so that should say list 1-1, and we end up with a mean of 60.71 and a sample standard deviation of 15.1185789. So now we've got a sale and all the prices are being halved. So instead of 35, we'd have 17.5. Instead of 50, we'd have 25. Instead of the 2 60s, we'd have 2 30s instead. Instead of the 37, sorry, instead of the 75, we'd have 37.5. Instead of the 65, we'd have 32.5. And instead of the 80, we would have 40. So I'm going to type those numbers into my calculator. going back into my calc, and I can see that my new mean, so this is for part 2, my new mean is 30.36 to 3 significant figures. So before, when we were multiplying by an amount, I said that for the mean, when each value is multiplied by the same amount, the mean is also multiplied by that amount. So does that still hold? Well, when the mean was multiplied by a half, was the mean, when each value was multiplied by a half, sorry, was the mean multiplied by a half? Yes, it was. Okay, so that holds for what we said before. Now for the standard deviation, we have ended up with 7.55928.946. Now, as we did before, we're going to have a look at the variance for this. So the variance for the first one would be 15.1185789 squared, which gives us 228.571428 for our variance. For the second one that we have here, we have 7.55928946 squared, which gives us 57.14285714. So if I do what I did before and I divide my old variance by my new variance, divide my new variance by my old variance, so divided by 228.571428, I get almost a quarter. Okay, so to get from our new variance, from our old variance to our new variance, we are timesing by a quarter, when with our data we were timesing by a half. So we're trying to think of what happens between 2 and 4 that is the same relationship that happens between a half and a quarter. And hopefully we're seeing that it's squared. 2 squared is 4, a half squared is a quarter. So if I go back to my prediction here, we are multiplying by the multiplier squared. When we have a look at the second Now You Try question, so to start off with, we're just trying to find the mean and the standard deviation for these faulty components. So I'm going to delete all the data I have in there. So 0, 1, 2, 3, 4, 5, 9, 12, 5, 3, 0, 1. Calc, remember that we now need to change this to tell it that we have a frequencies in list 2. And we're going into 1 var. So we end up with part A with a mean of 1.2 and a sample standard deviation of 1.1861267. Then it turns out, well, it was actually set up faulty, and there should have been 3 extra faults per day. So instead of 0, we should have had 3 faults. Instead of 1, we should have had 4. Instead of 2, we should have had 5. Instead of 3, we should have had 6. Instead of 7, we should have had 8. And instead of 5, we should have had 8. Sorry. Instead of 4, we should have had 7. Instead of 5, we should have had 8. So again, back in my data, I'm just going to change that first list. So we'd have 3, 4, 5, 6, 7, 8 instead. And this time, that gives me a mean of 4.2 and a sample standard deviation of 1.1861267. So when I was adding on a value before, so that was our first example on the last page, when each value increases by the same amount, the mean increases by that amount. Well, this time, the number of faults for each day was increasing by 3. And yes, we went from 1.2 to 4.2. So that has worked there. And we said that for the standard deviation, that when each value increases by the same amount, the standard deviation stays the same, and we have found that indeed the standard deviation has stayed the same here. So that gives us a couple of points which I've explained on the next page. So when we are adding or subtracting or multiplying all the values by the same amount, we have certain changes that happen to the mean and standard deviation. So when we add or subtract the same amount to each value of piece of data, the mean increases or decreases if we're subtracting by the same amount. So for instance, if we added 3 to each piece of data, the mean would increase by 3. When we multiply each piece of data by the same amount, the mean is multiplied as well by the same amount. So if we times each value by 3, we would have to multiply the mean by 3. For the standard deviation, if we add or subtract any values to each piece of data and it's the same amount, then the standard deviation stays the same, which also means that the variance will stay the same. And finally, if we multiply each value by the same amount, then we end up multiplying the variance by the square of that amount. And remember that it's the variance that we should be looking at to get that. And remember that the variance is the standard deviation squared.